Hello children, welcome back to the channel. Today we will be taking up the application part of the theories of moment of inertia that we have studied till now in my previous two videos, right? So in my last video what we have found or discussed is that the moment of inertia, the two laws or two theorems of moment of inertia, which are known as the law or theorem of parallel axis and the theorem of perpendicular axis, given by these two equations, right? So what we will do is that we will take certain everyday objects or special objects and try to find the moments of inertia of those objects about certain axis using this formula. And the first instance that we are taking will be of a ring. Now, a ring can be considered just like a circle, a linear mass distribution in a circular way. Okay. So, if we have a ring of given mass m, capital M, say, and we need to find the first is we want to find the moment of inertia of the ring about an axis through the center of the ring and perpendicular to the plane, which means the ring is lying on the plane of the board, so the axis will be through the center and perpendicular like this. So what will be the moment of inertia of the given ring in the plane of the board about this axis? Now for our convenience we can redraw this in the plane, like let's say we look at it from an angle. So this is the ring and this is our axis. Please remember this area is hollow. The entire mass is along the line only. It's a linear mass distribution basically. Okay, so if this is the ring here and this is the y-axis and here is the center which is the origin. Okay, y, that's right. So we want to find the moment of inertia of the given ring about the axis perpendicular to the plane and passing through the center. Now to do so, what we will do, we will first consider that what is the radius of the ring. Say, let's say we have the radius of the ring as r. Okay, and we will consider a small element of it here, whose length is given by dx, say. Okay, so if we take a small element of a disc or of a ring whose radius is r and mass is m, what will be the mass of the element? To find that, first what we need to do is to find what is the mass per unit length of the ring. Now what is the entire length of the ring? If radius is r, its length will be equal to its circumference, right? So the length of the ring will be 2 pi into r. And given that m is the mass of the ring, then m divided by 2 pi r will give us mass per unit length of the ring. Okay, so unit length of the ring has this mass. Then the element that we have chosen has a length of dx, so its mass dm will be given by this expression, mass per unit length multiplied by the length of the element. Then the moment of inertia of this element about the given axis, let's call this di, will simply be given by mass of this ring, that will be mass of the element, right, m by 2 pi r into dx. This is the mass dm into what is the distance? Distance is equal to the radius, right? It is at the circumference, so r squared. So to find the moment of inertia of that is I, what we need to do, we will simply need to integrate this expression with the proper limits. What will be the proper limits? The proper limits will be that we will start from x equal to 0 here and make a complete turn around the ring. So we will have to integrate it over the length of the ring. And what's the length of the ring? That is 2 pi r. Okay, so we integrate this with m r square by 2 pi r and then dx. Now the term in the bracket, capital M, R and 2 pi, all these are constants. So we'll take it out and we get m r by 2 pi, r square and r are there, so only this will be left. And then we have integration 0 to 2 pi r dx. Integration dx is x, so what we have? M by r 2 pi x 0 to 2 pi r. If we substitute the values, we will get mr by 2 pi into 2 pi r. So what we get is that moment of inertia of the ring about the axis passing through the center of it and perpendicular to the plane will be given by, if we simplify this, 2 pi will cancel, so mr square, so it will be mr square. This will be our required value, the moment of inertia of the ring about an axis passing through the center and perpendicular to the plane of the ring. Now we need to notice another thing is that the center of the ring, this point, if you see above this point, the entire mass is distributed symmetrically. If you take a diameter here, half of the mass will be this side, half of the mass will be that side, whichever you see. So what we will say is that the center, the mass is distributed symmetrically around the center, which means the center of this ring itself is the center of mass of the ring. We need to remember that. Okay, so this axis through the center and perpendicular to the plane will also be an axis through the center of mass and perpendicular to the plane of the ring. Okay. Now, another thing that we discussed in my previous video, that we have certain thing that is certain concept which is known as radius of gyration, which says that I equal to m into k square, where k is the radius of gyration and k is that distance where if the entire mass of the given object was concentrated, it will have the same moment of inertia as the given object, or with the about the same axis with the given distribution of mass. If you haven't seen that video, the link to my previous videos on rotational motion is given in the description below. You may please refer to that. Now if I have this, then what we can say is that mk square is equal to mr square, that is to say k equal to r. So radius of gyration for a ring about an axis through the center and perpendicular to the plane is equal to the radius of the ring itself, which means if we take the entire mass of the object, the ring, that is mass m, and place it at this point, say at a distance of r, then this mass m, its moment of inertia about the axis will be the same as the entire ring about the given axis. Okay, now we consider the same ring, but now we want to find the moment of inertia of the ring about one of its diameters. Okay, so we can have infinite number of diameters for a ring, right? It's a circle basically, so we have infinite number of diameters. So let's say we take one diameter like this, right through the center and coming down. Okay, so we want to find the moment of inertia about this diameter. Okay, now what we need to notice is that the diameter lies in the plane of the ring, and the previous expression that we found was for an axis perpendicular to the plane and passing through the center. So the diameter also passes through the center. Now previous expression was I equal to mr square, which was about an axis like this, right, perpendicular to the plane. Now what we want to do is that we want to find this, and this is the time when we are going to use one of these theorems. laws of parallel and perpendicular axis. Now you clearly see that this diameter is perpendicular to the previous axis of rotation, which was through the center and perpendicular to the plane. So what we will do, we want to make use of this law of perpendicular axis. However, to use that, what we will say, we have taken only one diameter. So what we can do, we can take another diameter which is mutually perpendicular to this, like this. These two are 90 degree. So what we are having three different axes. One is this axis, one is this, and then we have this perpendicular to it. So this was the z direction, or this was the y direction. So one of this will be x and one of this will be z direction, right? So now what we do is that we represent this as the z axis, the perpendicular axis is the z axis. So if I say this is z axis, perpendicular axis, then we will have two axes like this, and say like this. This will be x axis and this will be y axis, right? So two diameters are lying in the plane, and also we need to notice that about the diameter, any diameter, the ring is symmetric. So the moment of inertia of the ring about any of the diameters will be the same. So if we consider these two diameters as the x and y axis, which are mutually perpendicular to each other, and then z axis is perpendicular to the plane of the ring like this, then what we will have that, let's say this is x axis and this is y axis, and so z axis will be like this. So we can clearly use this particular expression. So what we will have is that I z, okay, I z will be equal to I say x plus I y. However, because of the symmetry, we already have said that the moment of inertia about any of the diameters will be the same. So let's call both of them as ID. So it will be I say diameter plus I diameter, which will give us that two moment of inertia, twice the moment of inertia about the diameter is equal to moment of inertia about the z axis, which is this axis, which is the axis passing through the center and perpendicular to the plane of the ring. However, we have already found this value. This value was mr square. So 2 the ID must be equal to m into r square. We are applying law of perpendicular, theorem of perpendicular axis here, which will give us ID equal to half m r square. So this is the value for moment of inertia of a ring about one of its diameter, any of its diameter, right? So we can write this here somewhere. I about a diameter is equal to half m r squared. Now we need to remember another thing about the radius of gyration. If we consider the radius of gyration here, what we have that ID must also be equal to m into k square, which is given by this. So we can rewrite this m r by root 2 whole square. Therefore, k in this case will be r by root 2. So radius of gyration of a ring rotating about its diameter will be r by root 2. We had already discussed in my previous video, or said that radius of gyration will depend on the orientation of the given axis about which it is rotating. And now we are having a different value for radius of gyration for the ring rotating about the diameter. For the ring rotating about the about the axis perpendicular and passing through the center of the ring was k was equal to r, and in this case k becomes equal to r by root 2. Alright. Next, let's find the moment of inertia of the same given ring about a tangent lying in the plane of the ring, which means we can choose any of the say, let's say this is the diameter. So we take a line parallel to it, touching this particular point, and this will represent the tangent, right? So what we need to do is that we want to find the moment of inertia about this tangent. So now what we have is that we already have the moment of inertia about the diameter, and we know that this tangent is parallel to the diameter, lying in the same plane. So we can call in the help of theorem of parallel axis. So what it says, theorem of parallel axis says that moment of inertia of a particle or of a body about a given axis is equal to the sum of the moment of inertia about the center of mass and product of mass and the square of the distance between the two parallel axes. Now this diameter will pass through the center. Since the diameter passes through the center, so this axis is passing through the center of mass. We have already discussed the center of mass of the ring is the center of the ring itself. And what is the distance between the two axes? Clearly it is equal to the radius, right? Tangent is at a distance of radius from the given diameter. So if we make use of this, what we will get? I about the tangent will be ICM we already have found, this is half m r square, right, plus m into d squared. What is d here? D is equal to r. So we have a plus half m r squared, or we have 3 by 2 m r squared. So this is the required moment of inertia about the tangent. See how easy it has become. We don't need to do all the complicated calculations. We already know the moment of inertia about the diameter, so we can directly get to the moment of inertia about the tangent in the plane. We already know the moment of inertia about an axis passing through the center and perpendicular to the plane. That's why we were able to find the moment of inertia about the diameter. So these two theorems are making it easier for us to find the values of moment of inertia of the same body about different axes, right? Now if this is so here, then again mk squared radius of gyration will be m 3r by 2 square root whole squared, right? R is not under square root. Therefore, radius of gyration this time will be root 3 by 2 r. See how radius of gyration is changing with the choice of axis. Okay. Now we also have another case. We can also have a tangent not in the plane but perpendicular to the plane. Why? See, we have an axis like this, z axis. We can always have a tangent passing through this, touching. What is the definition of a tangent? Tangent is a line that touches the circle at one single point. So we can always, if I have an axis like this, we can always have a tangent like this, right? Passing through one of the points. So let us say we have a tangent here, which is perpendicular to the plane of the ring. So what we are going to do is that we are next going to find moment of inertia of a ring about a tangent perpendicular to the plane. Earlier we have found tangent in the plane, lying in the plane. Here also this tangent which is perpendicular to the plane is actually parallel to the axis that was perpendicular to the plane and passing through the center, and center of the ring is the center of mass of the ring, right? So we can make use of this theorem and say that I dash t. Why we are saying dash? Because it is another tangent, not the same tangent as this, right? This tangent is perpendicular to the plane of the ring, must be equal to ICM. However, this ICM plus m d square. Now this ICM is moment of inertia about the axis perpendicular to the plane of the ring and passing through the center, and so this is mr square. So we have mr square plus m d, again the distance between the tangent and the axis through the center is r, so we have r square. So we have 2m r square. This is the moment of inertia about of the ring about an axis about a tangent perpendicular to the plane. If it is so, then we can clearly find radius of gyration mk square equal to 2m r square is equal to m into root 2 into r whole square. That is to say, k equal to root 2 r. So what we have found is that depending on the choice of axis, the moment of inertia of the same object ring is changing, and as it is changing, its radius of gyration is also changing as expected, as explained in our discussed in our previous video. Now let's say we have been given a thin uniform rod. What we mean by thin uniform rod is that its width is negligible compared with its length. In other words, what we are trying to say is that we can consider it as a linear object, and uniform means the mass distribution is uniform, so there is no gradient of mass. That is to say, any length piece of the rod taken, if the length is the same, then its mass will be the same. Let's say the length of the rod is L and mass is m. We want to find the moment of inertia of this rod about an axis which is perpendicular to its length and passing through the center. Let's say this is the center, and we have an axis like this which is perpendicular to the length of the rod. Okay, let's consider this the center as the origin. So what we are saying is that half of the length of the rod is lying in the positive x direction and half of the length is lying in the negative x direction. That is to say, this length is L by 2 and this length is also L by 2, which means if I say it's the x-axis, then x coordinate of this end will be L by 2 and this end will be minus L by 2. Okay. Now to find this, the moment of inertia about the given axis that is passing through the center, now we need to remember another thing here. Since the rod is uniform, so if I take the axis through the center, then center of the rod, about the center of the rod, half of the mass is to the left, half of the mass is to the right, which means that moments of masses will balance about the center of the rod. In other words, center of the rod is also the center of mass of the rod. Okay, which will come in handy when we try to find the moment of inertia about another axis. That will do in a while. Now let's say this is the case here. So how to find this? We can always say that at a distance of x from the center, we take a small element of length dx. This elemental length is dx. If it is so, what will be the mass of the dx? Let's call this dm, will be equal to mass per unit length of the rod divided by multiplied by dx. Mass per unit length of the rod will be m by L. Total mass is m and total length is L. So m by L will give us mass per unit length multiplied by dx. We have dm. So moment of inertia of this element about the given axis will be m by L dx multiplied by x squared. Right? X is the distance of the element from the given axis of rotation, or we can rewrite this as m by L x squared dx. We need to consider that m by L is a constant. So moment of inertia of the entire rod I will be given by integrating this expression. Let's take m by L outside the integration side because it's a constant, x squared dx with proper limits. Now what are the proper limits? We can clearly see that x starts from minus L by 2 and goes on to plus L by 2. right? So we can say minus L by 2 to L by 2. So once we find the value of the integrand, or after integration, what we'll get? M by L x cube by 3, then minus L by 2 to L by 2, or we can say M by L, L cube, 2 cube is 8, right? Let's take 3 outside, M by 3L. So we have, if we take 3 outside, we can rewrite this as x cube and this is as 3L, right? So x cube is L cube by 8, minus minus will give us plus L cube by 8, which is equal to M L cube by 4 and this is 3L. So the final result I, which will be equal to, one of the L's will cancel and 12, right? So ML squared by 12. This will be the moment of inertia of the thin uniform rod about the axis passing through the center and perpendicular to the length. And for radius of gyration, this must be equal to m k squared. Therefore, k squared must be equal to L squared by 4 into 3, right? Therefore, k will be equal to L by 2 root 3. Clear? So, I is ml squared by 12 and k will be L by 2 root 3. Now let's consider another axis which is passing through one end of the rod. Let's call, say, this axis, which is parallel to the given axis, of course. So we are talking about an axis perpendicular to the length and passing through the end of the rod. What will be the moment of inertia about this? We already have found I or ICM, right? We already said that the center of the rod is also the center of mass of the rod, so this will be ICM. So we can clearly use the law of parallel axis here directly, and we get I about the end will be M L square ICM ML square by 12 plus M into L by 2. That is the distance between the two given axes. So L by 2 whole square, which is, if I take M L squared common, we have 1 by 12 plus 1 by 4, right? Or we can write this as M L squared 4 by 12. That is to say, I will be equal to M L squared by 3, or 1/3 ml squared. So this will give us k square equal to L squared by 3 or k equal to L by root 3. See, again we have found different radii of gyration for different axes of choice. Now what we need to note here is that all the results that we have found are standard results and will find their application in problem solving. So you will be advised to remember all the given values, that is the moment of inertia of the different objects that we have discussed, ring and the thin rod, and also other standardized results for say a solid cylinder or a hollow cylinder, a solid disc, uniform solid disc, and also a solid sphere. All these things you can always find in any book. What are the moments of inertia for all these objects? What are the objects that we have said? Ring, disc, then we have said cylinder, cylinder, solid and hollow. Then we have said solid sphere, and we have also found rod. We need to remember the moments of inertia of all these objects about different axes. You can always find this enlisted in any of the reference books as a list. So please try to find a way to remember them, and that will be very, very useful in problem solving. We will see how in the next video, where we will be solving problems related to moment of inertia, and then we will move on from there. Okay.